Hello, everybody. Welcome today. So today is the first lecture of our little session on algebraic geometry. Previously, we've done like an art and reading seminar to just make sure that we're all on the same page with some abstract algebra 2 stuff. And now we get to kind of do the fun stuff. I am going to give a little preface that I just gave to Zach, Romeo, and Josh about like the syllabus that I've sent out in email, and maybe that's attached to this YouTube somehow. So I've had a recent revelation about Hartshorne that it is kind of not a great introduction to algebraic geometry, and that the second book that we're using is much, much better because it gives like exercises to work through that are background for everything that should go on in Hartshorne. And like just in the first section alone, we're going to go through it today just as like a primer on like, okay, here's why we care about the stuff that Bakil is going to build up. But for people who have never seen like algebraic geometry before, Vakil gives you a lot more background so that you can like read the page fluidly. When I first started like being interested in geometry, I tried to go through Hartshorne and I went very, very painfully slowly because I had to kind of find all these online resources and book resources, and that's just not a great experience. So yeah, all this to say, I'm motivated, and I don't know if this lecture will be public, which is why I'm on the old notes. I motivated earlier in the Arten seminar this business about classical algebraic geometry versus like modern, like what the point of modern algebraic geometry is. And a lot of the topics here repeat, and so I'm planning to go through this and then add on whatever I need to. So classical algebraic geometry is kind of asking questions about arithmetic functions or surfaces determined by arithmetic functions to a really large degree. And I think a good example of this is I was just at the joint math meetings, and like the closing talk for all the algebraic geometers was given by Janos Koyar at Princeton. And he gave a talk on this previously established result about how many straight line curves can lie on a certain object. And on the face of it, this is not like a very interesting question to ask. You would think like maybe there's infinitely many straight lines that could lie on something like, you know, a tetrahedron. But the answer is really like that it depends on the curvature of the surface and the smoothness of the curvature of the surface. And are there like deformations of surfaces that yield like the same number of invariant like straight lines versus, you know, like what degree of change in like contour can you make to an object to make that number change? And so the answer is that for many surfaces that we care about that have been classified algebraically, the answer is at most 27. I'm not going to pretend like I can explain that. It was a great presentation. A lot of it went way over my head. But these are kind of the questions that like classical algebraic geometry asks. But an interesting result is that that wasn't proven for a very long time. And there are still surfaces that are being classified for putting infinite straight lines on them. So I know Dr. Kolyar covered stuff up to like fifth degree polynomials and like in but so many dimensions. There are still things out there that people are researching. And so these are all kind of like interesting topics of study. Another example that I drew out here the first time I used these slides was like points on elliptic curves. How many rational points or how many integer valued points lie on a stretch of an elliptic curve, you know, or on the positive half of an elliptic curve. Another interesting question to ask that I didn't pose when I first did this is, you know, if you have points on an elliptic curve, or any curve for that matter, can you establish a general way to do pointwise addition on, you know, the x coordinates and the y coordinates and get another point on the curve? Moreover, if you can get such a thing, and we'll kind of we won't give it a name for a while, right? But if you can get such a kind of thing, what can the set of all such points tell you about the structure of the curve? What can it tell you about the differential information carried on the curve? You know, what information can be encoded in the zeros of a polynomial? Is there shared information between a bunch of zeros of polynomials? And so as classical geometers began to ask these questions, they had to kind of create tools to answer them. And so those tools at first started just with ideals and these notions called varieties, which we're going to talk about today. I know all three of you have already seen these things, so I'm kind of like preaching to the choir here, but maybe there's somebody watching this video who doesn't like attend our seminar and who hasn't heard of these things, so I'm going to kind of be redundant here. And so with ideals and varieties, these were kind of the first initial tools of attacking a lot of these problems. So a variety, a big generalization of it is it's something that's like the zero set of a collection of polynomials. We'll talk about irreducibility later, but for now you can think of it as the zero set of irreducible polynomials. The ideal of a variety is all of the functions, all the polynomial functions, which vanish on that set of zeros, right? So you can immediately think of the idea of an ideal of a variety encoding all of the polynomials which share roots. And so if you think back and you want to maybe construct more out of those functions, is there a way to garner unique data to each polynomial that maybe you get for like x cubed having a zero at the origin that x squared doesn't have? And so to do all of that, modern algebraic geometers developed like just an insane amount of theory to say basically, yes, there is a distinct way to store the fact that it has a zero at the origin and differential information. But how do you encode the differential information into something meaningful about like, you know, straight lines going through the origin on a curved surface? Okay, well now you get into embedding problems. And so all of this stuff kind of came down to asking questions that there wasn't math, you know, or tools to probe into, making new tools to probe into those questions, and then kind of interesting results falling out of the process of adding these things. So along that note, if T is, you know, a set of polynomials, we can think of what we'll call, when we're talking about Hartshorne, Z of T as the zero set of a bunch of polynomials. And so these are all of the points of K as an algebraically closed field, and K to the N is going to be, you know, n affine space, n-dimensional affine space over this field. And it looks like all of these tuples, P1 through Pn, that make points. And so this is our first characterization of affine space. And something I guess I don't say here is that affine space is interesting because it is invariant under linear transformation. So when we're thinking about, you know, n tuples of things, often we would just say, oh, well, that looks like a vector space. Maybe we can think of it as a vector space. Affine space and affine geometry works on the notion that everything is invariant under linear transformation. So what we are not worried about is angles between things, lengths of sides of things, or like location or centering. Anything can be moved around, anything can be stretched, anything can be re-angled. What we care about is the proportionality of lengths to each other. And even that is something that is like semi-variant under linear transformation. So, you know, maybe we care less about that. But like the sides of an object or the polynomial determining curvature, these kinds of things are questions that like can be posed in the framework of algebraic geometry. And this isn't to say that we don't use vector spaces. It's just to say that when you frame a problem in affine space, we mean that we are losing anything that varies under linear transformation. So algebraic sets are subsets of affine space that have polynomials which generate, or whose zero set generates that set. So like I was saying, the zero set of x squared is 0. But the zero set of x is also 0. And so, you know, the singleton set on the affine line, 0, is generated both by the zero set of x and the zero set of x squared. Do you care which one you pick? Maybe, but it depends on what you're trying to use it for. In this thing, I did a whole bunch of stuff explaining some topological notions that I'm just going to skip over. The important thing is we can define the Zariski topology on affine space, where closed sets are algebraic sets. So closed sets are zeros of polynomials, and open sets are complements of algebraic sets. And so, like, for example, on the affine real line, these are what closed sets look like, and then the orange stuff, and I don't know how visible this is, but like that is an open set, or the complements of the green points are an open set. We call a closed set irreducible if and only if there do not exist two other closed sets in I guess, closed subsets of A, such that A is their union. Irreducible closed sets are called varieties. And so what Hartshorne 1 kind of goes through is this relationship between maximal ideals and varieties. And in fact, the two do correspond. When we are going to go through Vikil, it won't be clear at first, but we're going to think about prime ideals as acting as points. And then we're going to think about other functions as acting as functions. And so we're going to evaluate functions at points by the division algorithm. And we're going to show that you can actually use that to derive your affine line, your affine plane, a lot of other notions that answer a lot of questions, but are all things that you're going to see in this lecture, just without a lot of wording and a lot of notation. So yeah, the ideal of a variety, like I said, is all of the functions which zero out on a variety. So again, my counterexample is that you could have a variety generated by x squared, and you might be thinking, okay, well, this variety is 0, I want this to mean x squared. Well, the ideal of that variety is going to be generated by x. And so you get x squared, x cubed, and so on. And so in a sense, you're maybe losing some information, right? If you're thinking of, if your variety is generated by the zero set of x, and then you take the ideal of the variety and you get the ideal, sorry, x squared. Let me move this around. You take the ideal of this variety and you get that it's generated by x. You might be thinking, well, there's some kind of failure of injectivity if you're taking a map from this over to now the set x squared, x cubed, ... and all of their linear combinations. So do we lose information? Kind of, but we'll see later that we get a lot of information back. Okay, yeah, so there's a proposition that just says that this is actually an ideal. And so, yes, the sum of two functions would vanish on a point, and then similarly, the product of some random function from your polynomial ring with something from your quote-unquote ideal of a variety vanishes because one of them goes to 0 and one of them doesn't. It's worth noting this is not function composition. I think there was some confusion about that the first time. This is, f at a point times g at a point. So, yeah. Okay, an important definition, like I said, is there's this idea of prime correspondence of ideals to points in affine space. And so, yeah, we have this notion that prime ideals are generated by irreducible elements of a ring, right? So you could have prime ideals in a number ring, and they would just be ideals generated by prime numbers. So like the ideal generated by 3 is a prime ideal, 7 is a prime ideal, 6 is not a prime ideal. It's easy enough to think about in terms of, in terms of modular arithmetic. If you wanted to evaluate 941 at, the ideal generated by 7, then you're really looking for its residue class, mod 7, and you would be able to use like the Euclidean and extended Euclidean algorithm to compute what its residue is. This is the kind of idea of evaluating number functions at number points. The same idea exists for polynomials, but we'll talk about that more in Vakil chapter 2 and 3. Okay, so yeah, do prime ideals correspond to irreducible polynomials, which correspond to irreducible algebraic sets, which are varieties? Yes. And so I guess the lead in here was to go to the Null-Stellensatz, and so this jumps really heavily. This is something Hartshorne does, and I guess that Arnton did, that I'm not really a huge fan of. I really like the way Vakil does everything. I'm a big fan of the book, and I got to meet the guy last week, and that was like the highlight of my life. So the Null-Stellensatz initially says if you have a polynomial or an element in an ideal, and there are certain assumptions about the ideal. Like, for example, we need the underlying ring to be commutative and etc. But if you have this element of the ideal, does there exist some S such that G to the S is in the ideal? Yes. So this is kind of the classical Null-Stellensatz. But there's a lot of different formalizations of the Null-Stellensatz. And then I guess we ended this by saying, Noetherian rings work nicely. So now, what I want to do is I want to motivate categories, and kind of why we care, how it helps us do geometry, and how to not get bogged down by how complicated this is about to get. So I want to preface this by saying I saw this kind of funny YouTube video from a guy who's a grad student on like undergraduates who obsess over category theory, and like basically the point was that some people can get really obsessed with like abstract nonsense that is not useful. And that can be a good thing if you have a lot of mathematical maturity and if you have like exposure broadly to big concepts in math. But like really until you've seen everything once and need to use it for something, it's not like a good idea to go worrying about like tensor categories or infinite categories or like any of these things that, are their own fields. We will use category theory in this seminar basically as a jumping off point for making life easier. And so kind of the rule that I want to follow is if we need it and we're going to use it for something, we should know what it is and we should know how to compute it, and we should know how it plays into the broader theme of making a geometric picture out of polynomials, ideals, and varieties. If it does not satisfy that condition, and it seems like it doesn't show up again for a while, we'll put a star next to it and we'll say, we're going to come back to this. And this goes for people who are going to be lecturing in the spring. Like, just keep that in mind when you're prepping your lecture notes. So let me start by defining what a category is. And I'm going to define it by showing you some examples of categories that you know really well. So groups, they have their own category. And their category has really two things in it when we think about it. It has objects, which are groups, subgroups, etc. And it has morphisms. And actually, it has homomorphisms. And with these objects and these morphisms, the idea is that we should be able to take any two groups and we should be able to have some kind of relationship between them with a homomorphism. Well, so what is the general structure of a homomorphism? Well, it says that if you have two groups, G and G prime, then phi from G to G prime should satisfy the condition that, AB gets sent to, and rather phi of AB gets sent to phi of A, phi of B, under whatever product is in the first group to the product in the second group. And we have this idea with homomorphisms that's kind of nice, that if phi is injective and phi is surjective, then we call phi an isomorphism. I'm going to make a remark. In a lot of categories, an isomorphism is not just a bijective map. In the nicer categories that we work with, it is, but it's very easy in like a little bit to construct some examples that do not have this kind of isomorphic structure. Often what we need an isomorphism to give us is an inverse. And so what we really need out of this is, for example, in topologies, objects are topologies and topological spaces, topological spaces, and morphisms are continuous maps. And morphisms are interesting in the category of topologies because they're specified by the condition that phi from T to T prime is continuous if and only if for every U open in T prime, phi inverse of U is open in T. So what we are preserving is we are preserving open sets. That's the underlying structure. Well, the same rules about injectivity and surjectivity still apply. And I just want to clarify that with category theory, this means injective. And this means surjective. So whenever you see this floating around somewhere, you can refer back to this. It's just kind of useful shorthand. I will also add, some people put the second arrow on surjective, like below. I can never get it centered, as is clear by the fact that that arrowhead is like miles off of the line. And so I like to put my arrowheads ahead of it, but that's just personal preference. Okay. But let's talk about isomorphisms in the category of topologies. So an isomorphism has the property that, okay, it needs to be a continuous map that's bijective, but it also needs to admit an inverse. And so obviously, like, this has an inverse image. But inverse image is not always typically an inverse because you could construct sets that do not have this property of continuity when you establish like a natural inclusion between them. And so it becomes this issue of, okay, we need to have an inverse for every single image. This kind of leads me to characterizing the category of sets. And this is an interesting one because it sets up our transition into the relationship between categories. So the objects are sets. They go up there. The morphisms are just functions. And so we know a lot about functions. They're kind of the easy case of all of these things we've just talked about, right? There are entire classes on group and ring theory. There are entire classes on topology. It's very rare that there's an entire class on sets. If you're going to see it, you're going to see it in discrete math for like a week. Set is interesting because it introduces this idea of a functor. And so this is going to be kind of the first formal definition, is that, no, I don't want to do this as a formal definition. I want to do this as an example. So the category of categories is called category. And its objects are things like group, topology, set, ring, module, etc. And its morphisms are called functors. And functors are interesting because they show us how these things relate together. And so my first example of a functor, before I fully define it, is that f, a functor from group to set, is this morphism which sends the objects of the group. So it sends ob G, if we're taking some specific group G, right, to its underlying objects in the set. So G as a set. We're forgetting the group structure. Forgetting. But it's not just going to send objects to objects. It's going to send the morphisms, the homomorphisms, to functions. So we're sending, and I want to kind of clarify this, we're sending groups to sets, specifically their underlying sets, but we're sending homomorphisms to functions. Now, this is one specific example. This is called the forgetful functor. So what do functors formally do? Well, they preserve some semblance of structure, sending objects to objects and morphisms to morphisms. Now, we're going to define formally next time what a category is. It's like an 11-point list. We're going to define the category of categories. This is meant to be an intuitive introduction to them, why they're useful, why it's worth sitting through like 4 weeks worth of category theory, because it can help us with geometry. So I'm kind of hand waving a bit this lecture, and hopefully that's okay. But I will establish some notation that's consistent, and that'll hopefully be helpful. So another example is another type of forgetful functor is f from some ring, and it's worth mentioning. I phrased this in total generality. Typically, a functor is from a specific collection of groups and their morphisms to a specific collection of sets and their functions. But like for example, if we have a functor from rings to groups, then what we can do is, we can say, all right, let's take the rings, let's take, the abelian group under addition, and let's send it to an abelian group under addition in groups, right? So what we're mapping is abelian groups under plus to abelian groups under plus, and forgetting the ring structure, right? Forgetting multiplication. Okay, so similarly, we could define, like a learning functor. Nobody calls it that. I totally made that up. That's a really dumb name. But we could define a functor that adds things, right? We could send rings to modules, right? This was like the last topic we talked about in Artin. We can send a ring R to the category of R modules, right? So like if R is a ring, then this gets mapped over to a set of R modules. So all of this is to say, we have a way to kind of dissect all of the math that you've ever seen into two kind of sub-objects, objects and morphisms. We have relationships that are presumably preserved between all of the things in a category, right? Like composition of functions works, associativity works. You have an identity morphism. Like these are things that we're going to formalize next time, but they exist and they're helpful and we expect them to be there. All of these things are things we care about preserving. Now, with functors and the category of categories, we have ways to look at how these things relate to each other. And so I will kind of take the example of like topological groups, right? Well, and I know this is not an algebraic topology course. It just lends itself to a very nice example. Consider like a circle. If we establish a base point on this circle, we're going to call the circle S1. It's a one-dimensional sphere. And we have a base point on the circle x0. There are really two types of loops that we can make. We can have trivial loops that go out and come back. And because there's no hole on the circumference of the loop, we can pull it back to just the base point. And that's a trivial loop. It acts like 0. But we can also make one full circumference of the circle and end up back at x. And what this acts like is, kind of a unit. And when we think about this in terms of adding loops to each other, we could go around once, twice, 3 times, 4 times, right? However many times we want. And we can think of it as adding 4 loops together. And so from this topological space that's a circle, and you can make a circle by identifying the interval 0, 1, where 0 is identified with 1. So this is a topological space on the real numbers. By identifying those endpoints, you can make a circle. By identifying loops on a circle, you can make a topological group. And it is the collection of loops on the sphere, or on the circle, under composition of loops. So you can go around, and if you set a direction, right, if the cardinal direction is counterclockwise, right, then we can go around this way, but we can also move back, and that's like subtracting a loop. So we have closure, and then we have inverses. We have associativity, right? If we do like add one loop, and then subtract a loop, that's the same thing as just doing one loop. So we have associativity. And then we also have identity, which is the first example I gave, which is a contractible loop, which doesn't go anywhere, right? So in this way, we have everything that we need to form a group. It's just not a way that you've maybe ever seen a group introduced, especially not the integers under addition, right? So this is like a very interesting example of a topological group, which is given not explicitly the way I said it, but it's given by a functor from a topological space to a topological group. And then, in turn, that topological group, which is called pi1, has a functor from topological group to group. Naturally, this commutes, and that's why I can just kind of say that this is isomorphic to Z under addition. My point is, for all of your math education, you've been working with different mathematical objects that fit together in interesting ways. And here we have a way to approach these things in abstraction so that maybe for any specific setup, we can get a universal property of how things fit together. You're familiar with a lot of these things, you just didn't approach it that way in like your initial education because it's a terrible way to initially learn about something. But once you're familiar with like topological spaces and groups and sets and rings, it makes a lot of sense. So about universal properties, I'm going to give two examples of a universal property. So universal properties, like I kind of led in with, are desirable because whenever we get a diagram that is, a collection of objects and morphisms and functors, we want to be able to say, this looks like this other thing, this behaves like this other thing. Any properties about this other thing should hold for this diagram. One such example is the product of sets. So if let x and y be in the objects of set, then the universal diagram of products is as follows. For anything to go from another set W into Y or into X, it factors uniquely through the product. So what does this mean? It means that, if you have W is like X Cartesian product 0, right? Or even the empty set. It just means that to send W into X, this happens by going to the product first in, X product Y, and then we come down to X. And this might seem like a dumb example. It's like, okay, yeah, sure. Cartesian products, we've seen this before, like theoretically, for any matrix, for one example, there's like infinitely many zeros going off this way, and the only reason why we don't show them is we specify the rank of our vector space, right? Or for modules, we saw that like you can chop off columns of zeros, and there was the whole weird proposition about like the ith row and the jth column. If if the ith column is the jth unit vector, then you can chop off the ith row and jth column. We saw that like, okay, theoretically for modules especially, there are just infinitely many zeros going in every single direction. The ones we care about factor through the Cartesian product. And so we really care about the non-trivial part of this. And in this case, that's x and y. This is not the only interesting example of a universal diagram. So there are these things called fibered products that are very useful because they encode data about how objects pull back from something. And this is going to make more sense when I give the thing. So if we have W as the general object, we have X, and we have Y, and we have Z, then the fibered product through Z is this thing. And the fiber product through Z has a universal property called a pullback. And so if you have a morphism alpha and beta from X to Z and Y to Z, then the fibered product is the set of A comma B in X product Y such that alpha of A is equal to beta of B. And so it's all of the things in the product, which is conveniently not written, but belongs somewhere around here. It's all of the things in the product that agree through these morphisms, alpha and beta, from X and Y individually going into the same thing. We often will use this notion indirectly whenever we say the words the pullback of, we're talking about the fibered product of two things. And the idea is that we're pulling back all of the things that agree in Z. So these are all very intuitive things that you've used and worked with and thought about, but not in complete abstraction. So I kind of want to just check in real fast to make sure everybody's happy with how things have been set up and motivated, and it's clear how this connects to geometry and to working with abstract geometric things.
Yeah, I think it's clear, Tim. You've actually done this in the topology seminar, but
Yeah.
yeah.
For people not in the algebraic topology seminar, and for potential viewers, is there anything that's unclear so far?
I think I'm good. Yeah, I think we're good.
Okay, cool. So from these notions, I'm trying to decide whether or not an example is more helpful, or going into a little bit of varieties. So in as much as today is supposed to be about Hartshorne, I'm going to define a few different types of varieties. This is going to seem totally orthogonal to what I was just talking about. And I'm going to motivate them in a way that will seem kind of random now, but in 2 months will come full circle. And so I'm just going to call this types of varieties. So we've talked about affine varieties. And these look like, n-dimensional tuples over a field K. And we typically note it as, the script A. And their main things are that they're closed, irreducible, or they're subsets of affine space. Closed, irreducible subsets under the Zariski topology. And so now I want to specify that we can have quasi-affine varieties. And what these are open subsets of affine varieties. And I think this is where I got confused the most in Hartshorne's chapter 1 was, we've talked about varieties entirely as this notion of being the vanishing set of a set of polynomials. And now we're saying that it is the complement of a vanishing set. Well, what it really is we're saying that if V of, F1 through Fs is the vanishing, then we are selecting, a subspace of this, and it is the does not vanish of, G1 through GT. Right, and I'll just say does not equal 0. And this is notation that we're going to use later. And the idea is that the relationship between, areas that don't vanish, that are subsets of varieties, maybe have something in common with ideals, and maximal ideals and prime ideals. And that these things will tie together in some kind of arithmetic way that makes it possible to compute meaningful things about varieties. Again, I'm being very hand-wavy here, and I'm kind of like teasing a bunch of stuff that doesn't show up for a little while, but it will be worth it when it does show up, I hope. So after our affine types of varieties, there are, of course, non-affine varieties. Oh, Romeo?
No, I'm sorry.
Okay. There are, of course, non-affine varieties. So one such type is a projective variety. So projective varieties, there's this really funny quote that's in Vakil when they first introduced projective varieties, and they do it well after affine varieties. It's this quote, I think, by the guy who came up with them, or maybe somebody who was like a very famous geometer back when they were first becoming popular. And the quote is that whoever decided that we should introduce numbers as coordinates clearly hated people. And what projective varieties are is, and I'll just talk about the projective line over a field K. The projective line is constructed by identifying points A and B with lambda A and lambda B for all lambda in K. So what's the real idea here? Well, it's something that's like invariant under scaling. But another construction of it is that it is n plus 1 copies of affine varieties. And then so-called homogenized basically by lambda. And so what this means is that when we say homogenized, we're looking at spots where, A and B don't vanish and are, invertible. We're not dividing by 0. And really, A comma B corresponds in the first slot as B over A, and in the second slot as A over B. I honestly still get confused with the intuition or visualization of projective varieties. And there's a big reason for this, is that the projective line is not a line, it is a two-dimensional thing. So the projective line adds a dimension because we're gluing an extra affine cell in. And that's just weird. No matter how you put it, that's just weird. What it does do is that it preserves the proportion of the things in our coordinates. It preserves the proportion of coordinates to each other. Another way to think about this is if you have to preserve coordinates between functions in a projective way, they have to be constant functions, because otherwise the proportion is going to change, and this criterion about, lambda does not hold anymore. And so when we think about projective curves, we're thinking about them in terms of disjoint unions of points. And so they become very interesting to study. And then, of course, quasi-projective varieties are open subsets of these n+1 copies of affine varieties homogenized by lambda and treated in the same way. And I'll just write those down so that they're there somewhere. But we're not going to worry about them for a very long time. I want to give, since we have 5 minutes left, another example of a non-affine variety that is going to be a big deal when we prove that it's not affine, but is not clear to see why it's not affine. And it's not a projective variety, so it's like a down-to-earth example. Examples of non-affine varieties that aren't implicitly projective. So the first big one is an infinite product of non-empty affine varieties. This is a non-affine variety, and this is something that we'll prove later on. Another example is the affine plane minus the origin. And then finally, my other example is the affine line with doubled origin. And what this looks like, and this is a very pictorial reference, what this looks like is gluing together two affine lines, and then at 0, we're going to jump over it 2 different ways. But we are going to glue the things together, and so what we actually get is that we have, you know, a 0 number 1 and a 0 number 2. And so we'll prove some theorems in chapter 4 of Vakil that will show that these are non-affine varieties, non-affine spaces, but are still like interesting and worth studying without having to get into the details of projective geometry. So I think this is a good start. I've given some examples, I've given some trivial examples, I've given some way too complicated examples, and I've given a useful example that is tractable but not too tractable. Same thing goes for categories and the category of categories and an intro to geometry. And all in all, I think that that is a good intuition builder. Any questions for the recording before we shut this off? Okay, so then go ahead mentally, if you care about the syllabus and you're looking at the syllabus, cut out the next 7 lectures of Hartshorne. We're not going to do those. We're going to start with Vakil on Thursday. We're going to go into universal properties, and we're going to formally define categories, but that shouldn't take very long. All right, I'm going to go ahead and pause or stop the recording, and thank you so much.